relationships and chemical reactions. Okay, so here's, let me close that, go back here. There we go. Mass relationships in chemical reactions. So we're going to be looking at specific reactions here, and we're going to be talking about mass relationships in those chemical reactions. So let's start looking at it here. So in chemistry, what are we concerned with? We're concerned with the microscopic world, and that's one of the things that actually makes chemistry kind of a difficult subject, is that, you have to use the macroscopic world, what you can see, to help you explain what's happening in the microscopic world that you can't see. You can't even see it under a microscope, right? Atoms and molecules are so small. Now, in terms of masses, now in the micro world, we can't take an atom or a single molecule or even 100 molecules and weigh them out on a balance. They're much too small. But in the real world, we can certainly think about grams. So we need to find a way to relate atomic masses to masses that we can, appreciate, and something that we can weigh out on a balance realistically in a laboratory. Now, the first definition we're going to look at tonight is atomic mass. And atomic mass is the mass of an atom in this special kind of unit called atomic mass units, which we abbreviate AMU. So that's the atomic mass unit. Now, if you're wondering, what the heck is an atomic mass unit? Well, there's actually a definition, like a universally, globally accepted definition of what an atomic mass unit is. And if you actually look up the history of it, and I can see you already rolling your eyes like, oh, no more history. Well, if you did look up the history of it, the definition of atomic mass unit has changed, I think, a few times over the course of history. But now the whole scientific community accepts that if you take one atom of carbon-12, you remember the isotope, so carbon-12 is an isotope of carbon that has 6 protons and 6 neutrons. If you take one atom of carbon-12, we say that that has an atomic mass of 12 atomic mass units. So what's an atomic mass unit, right? One atomic mass unit would be 1/12 of the mass of carbon-12, okay? So on this very small scale, okay, one hydrogen atom doesn't weigh exactly, one atomic mass unit. It actually weighs 1.008. And if you're already making a connection between these masses, these atomic mass units in the periodic table, you would be justified in doing so. Also, the mass of 16 oxygen atoms, for example, is 16 atomic mass units. Now, you might be like, okay, Mr. Dion, that's really cool. If I take 1/12 of this isotope, I get 1 atomic mass unit. Okay, great. And I see that you've put here what the atomic mass units for one hydrogen atom, or sorry, this shouldn't say 16 oxygen atoms. This should be oxygen 16. So let me just clear that up in case there's any confusion. I'll show you what I mean here. So this is hydrogen 1, and this is oxygen 16 is what they mean. Anyhow, you might be thinking, okay, well, what's so great about this? Because atomic mass units are so small. How can I relate that to grams? And I'm going to show you how to do that in just a second. Okay, so what's the take-home message? Is that an atomic mass unit is 1/12 of the mass of carbon-12. Okay, and we're going to look at how we can relate the atomic mass unit to grams. Okay, so the average atomic mass is the weighted average of naturally occurring isotopes of an element. So if you look at the periodic table, okay, for example, you'll see that for carbon, right, I just told you that carbon-12 weighs 12 atomic mass units, but carbon-12 is not the only isotope of carbon. There's actually carbon-12, okay, there's carbon, oops, didn't mean to do that. There's carbon-12, and there's also carbon-13. So there's 2 different isotopes. Now, where does this mass come from then? Where does this 12.01 come from? Well, like it says right here, it's a weighted average. And if you're like, well, what's a weighted average? Well, a weighted average means that 99, if you were to, grab a sample of carbon, right, 98.9% of the carbon does weigh 12 atomic mass units, but there's 1.10% of it that weighs 13, okay, atomic mass units. And you're like, well, how would I figure out this? Well, you just take a weighted average. So you would take 12 and you'd multiply it by 0.9890 and take 13 and multiply that by 0.00110, and you would add those together, and that gives you a weighted average. If you're still unsure about that, the best way to master that is to look at a problem. So it says here, Copper is a metal known since ancient times, is used in electrical cables, pennies, and other things. The atomic masses of its two stable isotopes, which are copper 63 and copper 65, are 62.93 atomic mass units and 64.9278 atomic mass units, respectively. What's the average atomic mass, okay, of copper? Now, if you have a periodic table near you, and I always have one up on my wall here, so if I go over to the periodic table, I look up copper, it's element number 29. Okay, so copper is element number 29 on the periodic table. Okay, and if I look up the mass that's reported beneath copper, it says 63.55. Okay, now that's the average of the isotopes. So that's the average of these two isotopes. And look at it. This isotope is not 63.55. It's actually lower than 63.55. And this isotope doesn't weigh 63.55. It's higher than 63.55. So it makes sense that the weighted average of these two should give us, you know, this number or something pretty darn close to it. Now let's check that out. Okay, so the best way to see if it works is to prove it. So I gave myself a little bit more room on this slide to do the math, which I've done some of ahead of time. Let's grab the old calculator here. So remember, if we have 69.09%, instead of writing out 69.09 divided by 100, I'm just going to do that math ahead of time. So if I take 69.09 and I divide by 100%, I end up with my percents canceling, and I move the decimal over this way. So I get 0.6909. And if I do the same thing with this one here, 100%, this cancels out, and I get 0.3091. Right? What happens if you add these two numbers? You should get 1, right? You should get the number 1. So these represent the fraction of 1 that each one of these isotopes represent. Now let's give it the old college try. So for copper 63, we have our atomic mass, which is 62.93 AMU, and we're going to multiply it by its relative abundance, which is 0.6909. Now let's take our calculators. We take here 62.93 times 0.6909, and you end up with 43.48. So 43.48 AMU. And you're like, Mr. Dion, that's nowhere near, that's nowhere near the atomic mass that's reported on the periodic table. Now, hold on. We have to take into account copper 65. So let's do the exact same exercise. So we have its atomic mass, which is 64.9278 atomic mass units, and we're going to multiply it by its relative abundance, okay, shown here, 0.3091. Oops. And when I multiply that out, so 64.9278 multiplied by 0.3091, I punch that in my calculator and I get 20.07. So 20.07. Of course, I'm only going to carry over 4 significant digits because both of these numbers have 4 sig figs. So when I tally that up, 20.07, 20.07 and 43.48, I end up with 63.55 atomic mass units. Okay, let's go back a slide. Okay, let's go back here. Well, looky. What did I say on the last slide? I said that when I looked at my periodic table, I saw a mass of 63.55, and looky, it's the exact same. So this checks out. So that is how you calculate the weighted average, and that is the mass that you see on the periodic table. So now you know when you look at a periodic table, like say for example, if you look at chlorine, it says that it's 35.453 atomic mass units. Well, where does that number come from? That's a weighted average of all of the isotopes of chlorine. And you can see how this lends itself to a very easy question for Mr. Dion to write for your next exam. I just give you some isotopes, their relative abundances, and I say, calculate. I ask you this thing here, calculate the average atomic mass. Give me a thumbs up if you follow me on this one. on calculating a weighted average to determine an average atomic mass. All right, thanks, Gabriel. Great. Absolutely good. Yeah, not meant to be anything mind-boggling, meant to be something enjoyable. So again, all of these atomic masses that you see on the periodic table, and Mr. Dion needs a new prescription pretty bad, so it's hard for me to read all these numbers. But you can see, like I told you, that for example, chlorine is 35.45, right? Let's say you look at hydrogen, 1.008. Where does that 1.008 come from? It comes from a weighted average of hydrogen 1, hydrogen 2, which is deuterium, and hydrogen 3, which is called tritium. Okay, so all of these atomic masses, most of them are weighted averages of 2 or more isotopes. Anyhow, now, I love all those thumbs up. You're like, yeah, I get it. Sounds good, Mr. Dion. Awesome. I can do this. Yeah, I'm great. I'm really happy about that. But, you know, we still haven't answered the question, how do we relate this whole AMU thing to number of grams, right? And an atomic mass unit is so exceedingly small. It's pretty close to the mass of one hydrogen atom. That is like almost unfathomable, you know, how small that mass is. You know, it's not the mass of an electron, but it's small, right? So how do we relate that to something that we can, you know, use in our everyday lives? And for that, I have to introduce the concept of the mole. Now, before we get into the mole, and I'm sure that some of you have studied high school chemistry before and have probably been introduced to the mole, which I know is a little rodent, you know, that digs holes underground. But in chemistry, the mole is something completely different. And we actually abbreviate the mole as MOL. Look at that. We dropped a whole letter, the letter E. Our chemists, you know, we really get a lot of work done. Anyhow, let me ask you guys a question. I know you're all paying attention here. What if I told you, here we said we have a dozen, right? You'd know that that's 12. What if we had a pair, right? If I said, give me a pair of shoes, you'd know I wasn't asking for 3 shoes. You'd know I'm asking for 2 shoes. I got another one for you. What if I said, give me a baker's dozen? Could anybody tell me how many are in a baker's dozen? Not a trick question. Just curious if anybody knows.
13.
Yeah, you're absolutely right. Yeah, thank you. It's 13. What about, I'll give you another one. Do you guys know how many are in a gross? Without Googling it. Does anybody know how many are in a gross? If I said, give me a gross of, donuts, how many would that be? Trevor says, sorry, let me scroll down, 144. Yeah. So a gross is a dozen. So it's 12 dozen. So yeah, a gross is 144. But that's not a word that we use a whole lot, right? We use the word gross, but maybe not in this connotation, right? Let me think of another one. What about a score? Okay. Does anybody know how many are in a score? How many would be in a score? This one you can Google it because it's not that commonly used. How many are in a score? Anyone? No? Okay. There's 20. Okay. So somebody said 7. Yeah, there's 20 in a score. So you're like, well, what's your point, Mr. Dion? My point is this, is that there are words that we use in our everyday parlance, that we use to represent numbers, okay? All the time. So a mole is nothing more than a word, just like all of these, a dozen, a pair. It's, a triplet, nothing more than that. It's just that a mole is a really big number, okay? And that number is this number right here, 6.0221415 times 10 to the 23rd power. It's a huge number, and we call that number, it's so big, instead of me always saying 6.02 times 10 to the 23, right? We call it Avogadro's number because it was discovered by somebody named Avogadro. Now let's back up to this definition here. It says the mole is the amount of substance that contains as many elementary entities as there are exactly atoms in 12 grams of carbon, okay? And what did we know about 12 grams of carbon, right? Okay, so we know that in 12 grams of carbon, we have 1 mole, right? 1 mole of carbon atoms. So if you were to add up 6.022, and I'm normally going to shorten it to, I'll usually just use 4 sig figs, 6.022 times 10 to the 23. If you had the time, which you don't, to measure out 6.022 times 10 to the 23 number of carbon atoms, it would weigh exactly 12 grams. Now, anybody could go over to a balance in a lab and weigh out 12 grams of something. That's pretty easy, right? So now we're going to see the importance of Avogadro's number. So let's see here. It says molar mass is the mass, and this is a definition that you have to be aware of. So let me highlight it here. Molar mass, and I'm going to say molar mass all the time today, is the mass of 1 mole of anything, whether it's eggs, shoes, marbles, students, computers, crummy iPads, atoms, molecules, doesn't matter, okay? But molar mass is the mass of 1 mole of something in grams. Now check this out. If we have 1 mole of carbon-12 atoms, we have Avogadro's number, 6.022 times 10 to the 23rd of carbon-12 atoms, and it weighs 12.00 grams. And we know that 1 carbon-12 atom weighs what? 12 atomic mass units, okay? So 1 mole of carbon-12, again, contains 12.00 grams of carbon-12. So that means that for any element, if you're like, what's your point, Mr. Dean? My point is this right here. For any element on the periodic table, the atomic mass units, right? The atomic mass is going to be the exact same as the molar mass in grams, okay? And if you're like, well, what's the significance of that? Let me show you. Let's back up here. You remember how I told you that all of these masses on the periodic table, they were atomic masses? Well, they're also molar masses. So let's just pick one, for example, and I'll pick one that I can maybe see here. Let's say we take neon, okay? If you look at the mass of neon, it says 10, that's the atomic number, neon, and then it says neon below that, and then it says 20.18. So it says 20.18, and I told you that that means that neon weighs 20 atomic mass units. Well, it also weighs 20.18 grams if you have 1 mole of neon atoms. I know I haven't lectured a whole lot here before I've asked for a thumbs up, but give me a thumbs up if you follow me thus far, because this is really important moving forward, okay? All of these atomic masses, if you take 1 mole of any of these elements, it's going to be the number of grams in 1 mole. Okay, good. All right, that's great, because that's going to be super important for the rest of the lecture. We kind of laid the foundation or the bedrock for the rest of the chapter. So this slide, it just shows you the relationship between mass and atoms that I just covered. Right? If you take the mass of an element and then you can convert that into the number of moles using the molar mass, and then you can figure out the number of atoms from that. Anyhow, and that's something that we're going to do a few times in this class. So let's take a look at an example and see if we can apply our newfound knowledge to solve a problem. So problem 3.2. Now, again, this isn't meant to be any kind of mind-boggling problem. Mr. Dion is not a fan of the trick question, but this is a question that would lend itself, very easy for me to make a question just like this for exam number 2. It says helium is a valuable gas used in industry, low temperature research, deep sea diving tanks, and balloons. How many moles of helium atoms are there in 6.46 grams of helium? So the way that we're going to solve this problem is I'm going to use what's called dimensional analysis, right? And I'm going to start out with what's been given to me. I know that I have 6.46 grams of helium. What I want to end up at the end, and I don't know how I'm going to get there yet, but I want to end up with the number of moles. And remember, we abbreviate moles as MOL, okay? I want to end up with the number of moles of helium atoms, okay? Okay, so the number of moles of helium. I'll just leave it as moles of helium, okay, because helium is an atom. All right, I'm just going to throw this out there, kind of throw you guys maybe a tough one. Could anybody tell me what I should do here? Does anybody have a strategy based off of what we've talked about this evening? Any strategies? Anybody have a strategy about what I might want to do here to get to the number of moles? Yeah, Julius made it really simple. He says divide by 4.003. Look, I get what you're saying, Julius. I'm going to have to explain it in even more detail, but I'm glad you're on the right page. Okay, so he's saying, Julius just threw it out there. He said divide by 4.003. And if you're like, what, divide by 4.003? How did he figure that out? Well, let's go over to the periodic table. If you look at the periodic table, and you're going to have to forgive me, I'm going to do my best here if you look at the periodic table, it gives you the atomic number of helium, which is 2. It's got 2 protons in the nucleus. But then below it, on my periodic table that I have posted on my wall anyway, it says 4.0026, which is close enough to 4.003. We usually use 4 significant figures, so Julius is 100% correct, okay? But that's what I see. Now, what is the significance of this number? What this number tells us is that we have 4.0026 grams of helium in what? 1 mole of helium. Look where we're trying to get to. We're trying to get to moles of helium, and we've got grams of helium. That sounds like a plan to me, right? Because if we set this up, okay, so that we put grams of helium in the denominator and moles of helium in the numerator, looky, I'm going to use this conversion factor right here, and I'm going to slap it in here. 4.003, okay? I'm just rounding here. Look at what happens, you guys. Grams of helium cancel out, and what am I left over with? The number of moles of helium atoms, okay? So if I take 6.46, I divide it by 4. I already went ahead and did the math on this one. What do you end up with? You end up with 1 point. I'm going to ask you guys first, can anybody tell me how many significant figures there should be in my final answer? Anybody? Bruce says, sorry, Bruce. Mauricio, Brittany, Bruce, Chris, they all say 3, and I agree. Deanna, and I agree with every darn one of you, okay? So it's going to be 1.61 is what I got, 1.61 moles of helium. There you have it. Now, before I move on, oops, I didn't mean to do that. Before I move on, I just want to ask you guys, give me a thumbs up if you follow me on that before we start blasting ahead. Okay, before we start moving on. Give me a thumbs up if you're like, yeah, that makes sense, using the molar mass from the periodic table. Okay, good. Again, we're still kind of laying, you're like, Mr. Dion, you won't stop with the bedrock. Well, we're still kind of laying some serious bedrock here, because in this problem, we only used one conversion factor, right? And we got that from where? We got it from the, starts with P, ends with periodic table. We got it from the periodic table. And moving forward, we're going to do problems where we use more than one conversion factor. So I want to make sure you're on the same page with me before we start, just kind of cruising along here. All right, let's take a look at another example. Lots of good examples to look at this evening. This next one here says zinc is a silvery metal that's used in making brass with copper. So brass is an alloy. It's just a mixture of copper and zinc. And in plating iron to prevent corrosion. How many grams of zinc are in 0.356 moles of zinc? I'm going to start this one off for us. I'm starting off with 0.356 moles of zinc. Can anybody tell me, I want to end up with grams of zinc. Could anybody tell me where I might find a conversion factor that would help me cancel out moles of zinc and give me grams of zinc? Not a trick question. Could anybody help me out with that? Somebody says periodic table. Somebody says Avogadro's number. So this question has nothing to do with Avogadro's number. To use Avogadro's number, that's when we want the number of entities. Now, what kind of entity is zinc? Zinc is an atom, okay? It's an atom on the periodic table. So the only time we would have to use Avogadro's number is if we wanted to know the number of atoms of zinc. But we want to know the number of grams of zinc. And so for that, we're going to go to the periodic table and we look up the molar mass of zinc. So zinc is element number 30. And so if I write down here, zinc 30, zinc has a molar mass of 65.39. So 65.39, and that's grams per mole. Okay, so we have 65.39 grams of zinc in 1 mole of zinc. Well, looky. My moles of zinc are going to cancel out, and I'm left over with grams of zinc. So when I take that 0.356, I multiply it by 65.39, I got 23.3. I'm going to double check my calculation. 0.356 times 65.39. 23.3 27884. So I round that to 3 significant figures, and I get 23.3 grams of zinc. All right. Good. All right. Perfect. All righty. Well, with that in mind, let's move this over. Do you guys enjoy the problem solving? All right. Julia says, yeah. All right. I do too. I really enjoy any kind of problem solving. Chemistry is one of those subjects where you can sit here and talk about it all day. But until you do some, like Victoria says, good practice, you'll never, it's very difficult to master. Now here's a problem. I don't want to blow the lid off, but here's a problem where we are going to have to use Avogadro's number. It says here the C60 molecule. So this is C60 right here. You might not have even heard of this molecule, but Sir Harold Kroto, I think he won the Nobel Prize for elucidating the structure or something of C60. It's they call it Buckminster Fullerene, kind of an interesting name. It's named after this architect, Buckminster Fuller. Anyhow, it says here, what's the mass in grams of one C60 molecule? Okay, just what's the mass if I have one of these? And yes, and you're like, if you're thinking, hey, that looks an awful lot like a soccer ball, it does. It does look just like a soccer ball. In fact, in my office at UCCS, I actually have a model of Buckminster Fullerene hanging from the ceiling. So something to look at there. So we can put here soccer ball. Maybe if anybody's a soccer player out there, you could count all the points on a soccer ball and make sure that they add up to 60 points. Anyhow, how much does one of these things weigh? Now, obviously, it's going to be an exceedingly small mass, right? Because it's only 60 carbon atoms, so that's not a whole lot, right? Anyhow, let's see if we can figure this out. We know that in one C60 molecule, okay, so that's what we're starting out with. Well, I know that in one C60 molecule, how many atoms of carbon do I have? How many atoms of carbon are there in one C60 molecule? Definitely not a trick question. This is meant to be a very reasonable question. How many atoms of carbon are there in a C60 molecule? Yeah, thanks, Brittany. Absolutely. She said 60? Yeah, absolutely. There's 60 carbon atoms. 60 carbon atoms. Okay. Well, how would I figure out the mass of one carbon atom? I know the mass of a mole of carbon atoms, right? If I go over to the periodic table, I see that carbon, it says 12.01. So that's 12.01 grams in one mole. Okay. But how many moles do I have here? I don't have a mole because a mole is 6.022 times 10 to the 23 carbons. I'm only talking about 60. That's not a whole lot. So we have to use Avogadro's number here, right? And we know that in one mole of carbon, we have 6.022 times 10 to the 23 atoms of carbon. Now, if I lost you here, let's slow down. Let's see what we've done. C60 molecule. We know that in one C60 molecule, we have 60 carbon atoms. I bet you figured that out in your brain, okay? Now, we know that in one mole, we have this many atoms of carbon, okay? So when you take 60, so if you're like, Mr. Dion, all you've done here is taken 60 and divided by this huge number. Yeah, that is all I've done, okay? Because if we were to stop right here, we would have the number of moles of carbon. You know what? Let me just do it here. Let's take 60 divided by 6.022 times 10 to the 23. I get 9.96 times 10 to the negative, or 9.963 times 10 to the negative 23. That's a really small number. But think about it. You've got to have Avogadro's number to have a mole. You don't have any 60 atoms. Are you kidding me? You're nowhere near a mole. Not even remotely close, right? You're so far away. So you have a really small quantity, right? You have nowhere near a mole. Okay. Now, I'm just going to put in the last conversion factor, which is I know that in 1 mole of carbon, I have 12.01 grams of carbon. Well, looky. the units, moles of carbon cancel out, and I'd be left over with grams of carbon. So if I take that small number that I had and I multiply it by 12.01, I still get another small number, right? I get 1.1966 something. So that rounds to 1.197. That's supposed to be a 7. 1.197 times 10 to the negative 21 grams. Does that make sense? Let's back up just for a second, okay? And I know you probably follow me, but again, I'm the teacher. I want to make sure you're with me, okay? Before we just keep ripping here. Think about it. When I have 6.022 times 10 to the 23, which is a huge number, atoms of carbon, right? That's equal to 1 mole, and that equals 12.01 grams. Okay? Compare this number. Okay? Compare these two numbers. This many atoms and this many atoms. Does that make sense? Hell yeah. Pardon my language. 60 is a much smaller number than this. So it makes sense that your mass isn't going to be anywhere near 12 grams, right? It's much less, okay? Give me a thumbs up if you follow me on that problem. Again, just manipulating using Avogadro's number. Okay, cool. Good. That's great. So another good practice problem. With that in mind, let's shift gears and let's talk about molecular mass. So far we've talked about atomic mass, right? If you go back, right, we talked about atoms of carbon. Here we talked about atoms of zinc. Here we talked about atoms of helium. What about molecules, right? What's a molecule? Well, a molecule is when we have two or more atoms combined together in a single entity. So it says here that molecular mass, which we sometimes call molecular weight, is the sum of all the atomic masses in atomic mass units. So let's say you have a molecule of, this is called sulfur dioxide, SO2. So I'll write it out here, right here. So SO2, this is called sulfur dioxide. Okay, so sulfur dioxide. So we have sulfur and we have an oxygen here. That's a molecule, right? That's a molecule of SO2, sulfur dioxide. So how would I figure out the molecular mass? I would simply add up all of the atomic masses. Well, what kind of atoms are in SO2? I have one sulfur atom, right? And I have two oxygen atoms. Okay, well, what's the mass of a sulfur? If I go over to my periodic table, sulfur weighs 32.06 AMU. There's one of those, okay? And oxygen weighs 16.00 AMU, and there's two of those. Now, if I take the product of both of these and tally them up, I should get 64.07 AMU total, right, for my atomic mass for one molecule. But I know that in 1 mole of sulfur dioxide, it's going to weigh that many grams, okay? Now, molecular mass is something that you're going to end up calculating probably, this is there's a little hyperbole here, but you're going to calculate it probably almost Avogadro's number of times over the course of this class, okay? So it's something you're going to do very routinely and very often. So make sure you're able to calculate molecular mass. So with that in mind, we've already calculated the molecular mass of SO2. I want to skip right ahead, and I want to try to calculate the molar mass of caffeine. If you had some cola, maybe you had some Coca-Cola today, or some coffee or tea or something with caffeine in it. Here's the molecular formula of caffeine. It's got 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. Is it just me, or is that a lot of atoms? Yes, it's a lot, but we can tally up those masses. Okay, so it's just a matter of, a little bit of multiplication and addition. So let's start with the carbon. If I go over to the periodic table, I see that carbon weighs 12.01 AMU, and there's 8 of those. Now remember, the 8 and the 10 and the 4 and the 2, those are exact numbers, okay? They have an infinite number of significant figures, and I've already gone ahead and done the math on this, thank goodness, that you end up with 96.08 AMU from your carbon. from your hydrogen, a hydrogen weighs 1.008 atomic mass units, and there's 10 of those, so multiplied by 10, and I end up with 10.08 AMU. Let's do the same thing for nitrogen. I'll go a little faster here. There's 4 nitrogens. Nitrogen weighs 14.01 AMU, multiplied by 4. I tally all that up. I get 56.04 AMU. And I do it again for oxygen, which has 16.00 AMU. And there's 2 of those. I get 30. Did I make a mistake here? 2 oxygens. I don't know why. I think I made a mistake here in my original math. Anyhow, let's see here. Let's tally all that up. So if I take my calculator and I add up 96.08 plus 10.08 plus 56.04 plus 32, I end up with 194.2 atomic mass units. That means that my molar mass, okay, my molecular mass is this, but my molar mass, I'm going to write that out too. The molar mass is equal to 194.2 grams per mole, okay? Anybody could go over to a balance and weigh out 194.2 grams of something. So again, you see how using molar quantities, right, molar masses, we're able to weigh out a number of molecules that we can grasp using Avogadro's number. All right, give me a thumbs up if you follow me on that one. I went over it pretty slow, I think. Not slow, but I'd say in a reasonable amount of time. Reasonable. Okay, thanks, Reagan. All right, great. Thanks, Gabriel. Perfect. Wonderful, wonderful. Good. Well, with that in mind, could I throw a problem to you guys and give you guys, would you guys appreciate it? This is something I don't do a whole lot of, but I will just ask. And if anybody wants to unmute or just type out, would you guys appreciate if I gave you, say, like 2 minutes to try a problem before I start solving it? Because just watching me solve problems is probably not ideal. Reagan says yes. Okay. I want to give you 3 minutes to take a look at this problem. 2 or 3 minutes, okay? I went from 3 minutes to 2 pretty quick, didn't I? I want you to take a look at this problem. I want you to read it, think about it. You all have the knowledge. You know, I've given you the facts, and you should be able to get an idea of how to solve this problem. It says methane, CH4, is the principal component of natural gas. How many moles of methane are present in 6.07 grams? I'll be right back. I'm just going to go get a drink of water. Oops. All right. That probably hasn't been 3 minutes, but I'll just throw it out there to my students. If anybody wants to unmute their mic or type it out in the chat, does anybody have just kind of any strategy that they could throw at me here before I start writing things down? Yeah, Reagan says, calculate the molecular mass or the molar mass, absolutely, of methane, then do dimensional analysis to convert it to moles. Reagan, I couldn't have said it better myself, and I've been teaching chemistry for years. That's perfect, okay? So let's take a look at what Reagan is saying, okay? What she's saying is this, and I'm going to slow it down a little bit, Reagan. She's saying you got 6.07 grams of methane, CH4, okay? And you want to end up somehow with the number of moles of methane. Okay, that means that your conversion factor has to have grams of methane and it has to have moles of methane on the top. Well, where would we get that? All we have to do is work out the molar mass for CH4, right? We just have to work that out. I'm going to do it a little bit quicker this time, a little bit quicker if we want to calculate the molar mass of CH4. We have 12.01 grams per mole for our carbon atom, right? There's only one carbon. And then we have 1.01 grams per mole for our hydrogen, and we have 4 of those. You tally all that up and you get 16.05 grams per mole. So that's the molar mass of methane. Now let's plug that in. We have 16.05 grams of methane in 1 mole of methane. Well, looky. My units, grams of methane, cancel out, and I'm left over with moles of methane. Is this not a beautiful thing? And so when we work all that spinach out, we end up with 0.378 moles, so 0.378 moles of methane. So what did we do here? We connected the concept of calculating a molar mass and using molar mass and a mass to determine the number of moles. That's a lot of moles and masses and M words, but we're basically connecting 2 concepts that we've already looked at this evening, okay? So we end up with this many moles of methane. Give me a thumbs up if you follow me that far. I know I'm asking for a lot of thumbs ups, but again, it's a very important section of this class because chemistry is an additive subject, right? It's going to keep adding on this, and we're going to use these kinds of calculations many times throughout this course. Well, let's do it again. It says here, how many hydrogen atoms are present in 25.6 grams of urea? What do you think? Should this be a big number or a small number when we determine the number of hydrogen atoms that are present in 25.6 grams? What do you think, big or small? If you're thinking like big or small with respect to what? I mean it, big or small. Will this be a big number or a small number? Our final answer. Who could tell me? Somebody must have an educated guess on this. Let me see, maybe I didn't scroll down far enough. Yeah, 2 people say big. You're absolutely right. It's going to be a huge number, right? Okay, because if you just read the question, it says here, how many hydrogen atoms are present in 25.6 grams of urea? They give you the molecular formula of urea. They tell you what it's used for, but then they tell you the molar mass is 60.06 grams. So 25.6, like this is just a rough approximation, but that's almost half a mole. How many are in a mole? Avogadro's number. So this is going to be about half of Avogadro's number. It's still going to be a huge number, right? All right. And I'm even making a mistake here because I haven't even taken into account that there's more than 1 mole of hydrogen atom. So it's actually going to be a number that's bigger than Avogadro's number. And if you're like, what? How do you know, Mr. DM? Well, let me show you. Okay. Let's walk through this one as a group. We're starting out with 25.6 grams of urea. And the first thing we're going to do is we're going to use the molar mass that's provided, which is we know that there's 60.06 grams of urea in 1 mole of urea that was provided to us. Look, if we were to stop right here, what would we have? The number of moles of urea. Now, we need a conversion factor now that we have not looked at tonight, but I want to just throw this out here. In 1 mole of urea, who could tell me how many moles of hydrogen atoms are there? Could anybody tell me how many moles of hydrogen atoms there are in 1 mole of urea? Not a trick question. Just look at the formula. And could anybody tell me? Somebody says 4. Yes. Bruce says 4. He's absolutely correct, right? Because if I have a subscript 2 here, that's the same thing as saying I have 2 NH2. So if I have 2 times NH2, that means I have H2 times 2, which means I have a total of 4 H's. So that means that in 1 mole of urea, I have 4 moles of hydrogen atoms. Remember, urea is a molecule. Okay, so in that molecule, there happens to be more than 1 hydrogen atom, right? In one molecule of urea, right, there's 4 hydrogen atoms. So it means that in 1 mole of urea, there's going to be 4 moles of hydrogen atoms. So look, if we were to stop right here, let's see, moles of urea would cancel out, and we'd end up with moles of hydrogen atoms. That's not what they're asking for. They're asking us for the how many hydrogen atoms are there? This is another stretch. I want to ask you, could anybody tell me where I would get a conversion factor to figure out the total number of hydrogen atoms? Where would I go to find the conversion factor? Not a trick question. Mr. Dion doth not like the trick question. This is not a trick question in any way, shape, or form. Who could tell me? Maybe I need to scroll down here. Where would I get a conversion factor that's going to give me the number of hydrogen atoms? Look, I'm looking for number of H atoms, okay? Maybe I should just put here hydrogen atoms instead of number of. Not from the periodic table, no. Where would I get something that's going to have moles of hydrogen atoms down here, and then the number of hydrogen atoms on top? What did Chris say? Avogadro's number. Absolutely right, because in 1 mole of hydrogen atoms, I have 6.022 times 10 to the 23 hydrogen atoms. Looky, looky. Now my moles of hydrogen atoms cancels out here, and I'm left over with the actual number of hydrogen atoms. And so when I put all that into my calculator, I end up with a really big number, which is 1.03 times 10 to the 24th power hydrogen atoms. Okay? Just going off your response, it didn't seem like anybody was too quick on this conversion factor. But remember, Avogadro's number is the number of entities in a mole. Okay? Does that make some sense? Does that clear it up a little bit now that you've seen it? How to use Avogadro's number to get the number of entities? I know that sometimes it's a stretch. It's hard to wrap your head around, Avogadro's number sometimes. All right. Well, anyhow, we're going to look at, many examples throughout the class. I have many practice problems where you can revisit this before the next exam. All right, let's switch gears and talk about something called formula mass. Right, you notice how so far all we've talked about is molar mass and atomic mass and molecular mass, right? We looked at all those kinds of things, but we haven't talked about something called formula mass. Now, the reason why we haven't introduced the concept of formula mass, because formula mass is used for ionic compounds, okay? Formula mass is the sum of the atomic masses in the formula unit of an ionic compound. And if you're like, well, no, what's a formula unit? Now, something I never want you to say is a molecule of sodium chloride, okay? Because sodium chloride is an ionic compound. What's an ionic compound made from? It's made from a metal and a non-metal, okay? A metal and a non-metal combined. There is no such thing as a molecule of sodium chloride. And you're like, well, how am I supposed to know that? Because you know that sodium chloride is made from a metal, sodium, and a non-metal, chlorine. And ionic compounds do not exist as molecules. If you're like, well, how do they exist? They exist as what is shown right here. They exist as what is called a crystal form. Sometimes we call this a crystal lattice. Now you can see here that I have all the chlorides, right, Cl minus, and all the Na pluses. Now I'm not going to fill them all in, but look, how many do we have here? We could tally them all up. I don't feel like doing that. But you can hopefully see relatively easily that the ratio of chlorine to sodium is a 1-to-1 ratio. And so that's the smallest whole number relationship between sodium and chlorine. And we call that a formula unit, okay? Because if you were to write, now I shouldn't try to confuse you, but if you were to write Na10Cl10, okay, it's still a 1-to-1 relationship, sure, okay, but it's not the lowest whole number relationship that you could have, okay? So that's what a formula unit is. Now, if I add up the atomic mass of 1 sodium and 1 chlorine, what do I get? I get 58.44 atomic mass units. That means that 1 formula unit of sodium chloride weighs 58.44 atomic mass units. But what do we remember from earlier on in the lecture? That atomic mass units are equal to the number of grams in a mole. So that means that 1 mole of sodium chloride is going to be equal to 58.44 grams. And if you're thinking, Mr. Dion, that's not complicated. All I have to do is the exact same thing I did the last time, right? I add up the mass of a sodium, I add up the mass of a chlorine, and there you go, molar mass, okay? Hold on, okay? It's not, this is a molar mass, and we call it a formula mass. I just want you to understand what a formula unit is before we keep going. I'm going to skip the part about mass spectrometry because I'm never going to ask you anything about mass spectrometry in this class. And I want to switch gears and talk about percent composition. Now, this is not meant to be anything mind-boggling percent composition, but you have to understand what percent composition is. And percent composition of any element in a compound is defined as this, okay? So we take the number of moles, okay? So N, I just want to highlight what small n is. So you see the little n here. N is the number of moles of the element in 1 mole of a compound. So n is the number of moles of the element. Okay, we multiply that by the molar mass, grams per mole. We end up with the number of grams of that compound, or that element in the compound, and then we divide it by the entire molar mass of the compound. And then we multiply 100%, and that gives us the overall percentage of that element. If you're like, what? What do you mean? Okay, best way to learn it is with a practical example. Let's take a look at this molecule right here. This is ethanol, okay? This is the molecular formula for ethanol. And you're like, the same ethanol that's found in like Coors Light? Yes, the same one. The same ethanol that's found in gasoline? Yes, the same one. You shouldn't drink gasoline though. Okay, that's poison. Anyhow, all right, so here's the molecular structure of ethanol. So if I asked you to calculate the molar mass of ethanol, I know you could. What would you do? You'd add up the mass of what? 2 carbon atoms, 2 times 12.01. You'd add up the mass of 6 hydrogens, 6 times 1.008, okay? And then you'd add up the mass of an oxygen, 16. When you tally all that up, what you would end up with is, you'd end up with a mass which is 46.07 grams per mole. The reason I didn't do that with you is because we did it a couple of times already this evening. And you can see that the denominator for each one of these calculations just happens to be that number, because in 1 mole of ethanol, we have 46.07 grams. All right, so now we have established where the molar mass of ethanol comes from and where those denominators come from. Now, if I want to figure out the percent composition of carbon, what percentage of ethanol is made up of carbon? Well, I know the atomic mass of carbon, and I know that in my ethanol molecule, there's 1, 2 carbons. So I multiply the atomic mass of carbon by 2. I divide that by the total mass of my compound, multiply that by 100, and I end up with that carbon is actually, ethanol is actually 52.14% carbon. I can do the same exercise for my hydrogens. Look, in ethanol, there are 1, 2, 3, 4, 5, 6 hydrogens. So what am I going to do? I'm going to take the atomic mass of hydrogen, multiply it by 6. Then I'm going to divide that by the total mass of the compound, and I should end up with 13.13%. Okay, I do the same thing for oxygen. All of those, when you tally them all up, what should they equal? They should equal 100%. Give me a thumbs up if you follow me on this one. Just the percent composition. Sometimes this is called the percent by mass. of an element in a compound? Yeah, right. I hope you're encouraged by the fact that I don't even know you guys, right? I don't know you that well, but I am 100%, and I mean it, 100% confident that every single person who is hearing the sound of my voice can add numbers together and multiply numbers together and divide numbers. I know you're all capable of doing that. There is not any math here that is complicated. Any bit of this math could be done by somebody in junior high with a calculator, right? What's the difference? The difference is wrapping your head around what did I mention in the first class or the first slide this evening. Thinking about things on the atomic scale is not always evident, I would say. It's not always intuitive, okay? And that's what you're really training yourself to do here, right? That is, one of the keys of chemistry is somebody understands chemistry, they're able to think of something that they can't even see and understand it, okay? Something you can't see with your naked eye, and you're able to wrap your head around that. Now, if you're like, I need some more wrapping, Mr. Dion, I need some more, wrapping my head around it. Well, let's take a look at an example here. It says, let's say you have phosphoric acid. They give us the molecular formula for phosphoric acid. Here's the structure over here. This is H3PO4, okay, phosphoric acid. It's a colorless, syrupy liquid used in all kinds of things, detergents, toothpaste, and it's found in carbonated beverages. Anyhow, it says calculate the percent composition by mass of hydrogen, phosphorus, and oxygen in this compound. I'm going to go ahead and give you the molar mass of H3PO4. So the molar mass of H3PO4, I've already done it, is 98.00. 98.00 grams per mole. Would you guys like me to give you 2 minutes to try this one to see if you can figure out the percent by mass or the percent composition of these elements? How about you take 2 minutes, just get the old calculator out, some scratch paper. You only need a napkin and a pencil, and give it a shot. So I'm going to give you 2 minutes to give it a try. All right. Can I just ask, was anybody able to determine the percent composition um, of any of these elements? Can anybody throw out one element and say, hey, I figured this one out. I figured this one out. I'll take anything. Anybody? Hey, thanks, Trevor. Thanks, Julius. Hey, good. And they both did different elements. Great. So let's see. Trevor says for oxygen 65.31. That's what I got. And Julius says 31.6 for phosphorus. Well, they've already done all the work, so all we have to do is add those two and subtract them from 100. We've got the answer for hydrogen. Let me show you how Trevor and Julius arrived at these numbers. So for our oxygen, in H3PO4, right, you can see that there are the red atoms represent the oxygens, and there is 1, 2, 3, 4 oxygens. So I take 4 times the mass of an oxygen, which is 16.00 grams per mole, okay? So grams per mole, and I divide that by 98.0, what was it? 98.00 grams per mole. That cancels out. I multiply by 100%, and I end up with 65.31% oxygen. I do the same thing. So Julius, for phosphorus, he said the same thing. There's only one phosphorus in the whole molecule. And so phosphorus weighs 30.97 grams per mole, and he divided that by 98.00 grams per mole. And that cancels out, multiply by 100%. And I ended up with 31.60, which is what he got. And then for hydrogen, so for hydrogen, there are 3 hydrogen atoms. And so 3 times 1.008 grams per mole, like that. And then we divide that by 98.00 grams per mole. And we multiply by 100. And we end up with 3.09% hydrogen. And if you want to check your math, all you have to do is tally up those 3 numbers. So if we take 65.31 plus 31.6, I know it's correct, I'm just double checking it, 3.09, we end up with 100. And so we add that all together and we get 100.00%. There we go. All right. Again, you can see how I could pick literally any molecule on the face of the planet and just say, hey, give me the percent. I could give you glucose and just say, what's the percent composition of carbon in glucose, right? Or whatever. So a good thing to be able to do is calculate percent composition. Now, percent composition here and empirical formulas. Before we move on, I want to remind you of what an empirical formula is. An empirical formula is the simplest whole number ratio of the elements that are found in a molecule. Let me give you an example. Let's say you have this molecule, which I just mentioned, which is glucose. The formula of glucose, the molecular formula is C6H12O6. That is its molecular formula. So molecular formula. The empirical formula of glucose is the simplest whole number ratio. Now you can see here that in glucose, the ratio of carbon to hydrogen to oxygen is 6 to 12 to 6. Could I simplify that further? Absolutely, I could. I could break that down to 1 to 2 to 1. That's the simplest whole number ratio I could have for those 3 numbers. And how did I get that? I divided them all by 6. And so the empirical formula of glucose would be CH2O. That would be its empirical formula. So again, empirical formula is the simplest whole number ratio of the elements found in a compound. Now what we can do is we can use percent composition to help us determine molecular formulas. And if you're like, well, how would I do that? If you're given the mass percent, what we just calculated in the last problem, what you would do is you would assume that you have 100 grams of a sample. So you'd assume 100 grams of whatever molecule that you're talking about. Then you would take the number of grams of each element and you divide it by the molar mass. Well, that would give you the number of moles of each element. So now you would have a ratio of the number of moles. So let's say you had, glucose, you'd have CXHY, OZ, right? You would have these numbers, but they wouldn't necessarily be 1 to 2 to 1 or 6 to 12 to 6, okay? They would be some kind of fraction, and then you would divide each one of them by the smallest number of moles, and then you have to manipulate those to change to integers, right? What's an integer? It's a whole number, 1, 2, 3, 4, right? Okay, now if you're not entirely sure about what I'm discussing here, let's take a look at a problem where we do just this. We take percent composition and we determine empirical formula. It says here that ascorbic acid or vitamin C can cure scurvy. It's composed of 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. Now let's say if you had a 100-gram sample, assume 100-gram sample of vitamin C, that would tell you that you've got 40, in that 100 grams, you'd have 40.92 grams of carbon. You would have 4.58, you'd have 4.58 grams of hydrogen, and you would have 54.50 grams of oxygen. You're like, okay, I get it. I have this many grams of everything, but that doesn't tell me about the number of moles, right, in my vitamin C, which is going to have some kind of formula C, X, H, Y, O, Z, right? We still got to figure out what X, Y, and Z are. How are we going to do that? Because these are numbers of what? Moles, not grams. Can we convert from grams to moles? Well, you bet your Bobby socks we can, okay? Let's start with carbon. And for carbon, we take 40.92 grams of carbon. And in carbon, there are 12.01 grams per mole of carbon. Look, grams of carbon are going to cancel out, and I end up with moles of carbon. And so I end up with the number of moles of carbon as being, I've already done this, 3.41 moles of carbon. Okay, now we're going to do the same exercise, the exact same calculation for hydrogen and oxygen. So let's do it now. For hydrogen, okay, I have 4.58 grams of hydrogen. I'm going to divide that by 1.01 or 1.08 grams per mole of hydrogen. Grams cancel out. I end up with the number of moles of hydrogen, which is 4.53 moles of hydrogen. And lastly, we'll tackle oxygen. And we have 54.50 grams of oxygen. I divide that by the molar mass of oxygen, which is 16.00 grams per mole of oxygen. Cancels out. I end up with what? 3.41 moles of oxygen. Now look, there is no such thing as C 3.41, H 4.53, O 3.41. Does not exist. So scratch that, okay? So how are we going to figure out whole number ratios for these three numbers that I have shown here? Well, let's do the math. It told us in the last slide that we should divide by the smallest quantity. The smallest quantity happens to both be 3.41. If I divide this number by 3.41 moles, if I divide this number by 3.41 moles, if I divide this number by 3.41 moles, what do I get? I'm going to get 1 carbon, I'm going to get 1.33 hydrogen, and I'm going to get 1 oxygen. Now, what can I multiply all of these by? Because there's no such thing as 1 carbon, 1.33 hydrogens, and 1 oxygen. That doesn't exist. Okay. How could I massage those numbers? Well, what if I took 1.33 and I multiplied it by 3, right? Then I'd get 3.99, which is pretty darn close to 4. So if I took all of these numbers and I multiplied them by 3, I would end up with 3 carbons, 4 hydrogens, and 3 oxygens. That would give me this formula, C3H4O3. That is the empirical formula of vitamin C, or ascorbic acid. Now, I've already gone ahead and looked at the formula of ascorbic acid, which is right here, and you probably figured it out already. And the actual molecular formula is C6H8O6? Well, is C3H4O3 the empirical formula of C6H8O6? Absolutely it is. You divide all of this by 2 and you get the simplest whole number ratio of those elements. Give me a thumbs up if you follow me on this one. Determining an empirical formula, not necessarily a molecular formula, but an empirical formula. Thanks, Reagan. All right. Not mind-boggling math. Everybody can add, everybody can divide. What's it about? It's about relating things that are on the atomic scale to things that are on the macroscopic scale, things that we can weigh. Look, I know it's 6:46. You're probably tired of listening to me talk, but what do you say we try one more problem? One more problem. Example 3.10. Let's give this one the old try here. It says here, chalcopyrite. They've given you the formula. Is a principal mineral of copper. Calculate the number of kilograms of copper in 3.71 times 10 to the 3 kilograms of chalcopyrite. I would like to give you 2 minutes to see if you can solve this one. Okay, the first thing I would do is figure out the formula mass, because you're going to need that to get the number of moles. Okay. Yeah, I would do that. All right, I'll give you a couple of minutes to see what you can come up with. Look, if we were face to face, I'd run around the classroom and see what you're doing. But on account of the pandemic, we'll leave it like this. I'll give you a couple of minutes and see if you can come up with some kind of strategy for solving this problem. All right, I'm going to throw it out there. Does anybody have a strategy for this one? I'll take anything. Even the first step. Find mass of copper. Yeah, you definitely need the mass of copper, Madeline. Couldn't agree more. Yeah, because what you're going to do is you're going to multiply this mass of the mineral, right? You're going to all you have to do in this problem is nothing more than multiply the percent composition of copper by this mass and you're done. That's all you're doing, right? Because if you have this many kilograms of the whole mineral, which contains what? It contains copper, iron, and sulfur. All you need to know is the percent composition of sulfur in the whole darn thing and multiply it by that mass and you are done, okay? That is it, nothing more. In fact, let's do it. Let's find the percent composition of copper in this mineral. Now, I've gone ahead and I've calculated the formula mass of this compound. So the mass of a copper, so copper, as Madeline said, you got to look that up. It's 63.55 AMU. If you want to, and if you're like, I wanted to write grams per mole, do that. It doesn't matter. You're going to end up canceling them out anyway. Iron weighs 55.85 grams per mole. There's one of those. For sulfur, there's two of those. So 2 times 32.07 grams per mole. Okay. You work that out. You tally all those up. And I ended up with 183.54 grams per mole. Okay, for my chalcopyrite, which is CuFeS2. Now I want to find the percent of copper in this. Well, there's only one copper atom in the whole thing, so it's going to be 63.55 grams per mole divided by 183.54 grams per mole for the whole thing. So that's going to give me the percentage of copper in the entire thing. Now I'm going to do the math here to double check myself. 63.55. Sorry, my calculator's really loud when I punch on it. 183. Oops. 63.55 divided by 183.54. And I end up with, I could multiply it by 100% just for fun. You end up with 34.62. Oops. Mr. Dion, what are you doing? There we go. Multiplied by 100%, and you end up with 34.62% copper in that mineral, okay? But we can express that as a fraction out of 100%, right? And then it would just be equal to 0. Or a fraction out of 1, I should have said, equals 0.3462. So literally all I have to do is multiply this. It says here, I have 3.71 times 10 to the 3 kilograms of CuFeS2. And I know that there is 0.3462 parts copper in one molecule of chalcopyrite, like that. Okay, boom, and boom. I multiplied those out. What am I left over with? Kilograms of copper. So let me check here. 3.71 times 10 to the third multiplied by 0.3462. And I end up with this number, which should only have 3 sig figs, which is 1.28. Oops, get rid of the highlighter there, which is 1.28 times 10 to the 3 kilograms of copper. All right. Thanks, Gabriel. Thanks, Madeline, for the help. Okay. Does that seem helpful, that problem there, to my general chemistry students? We did a lot of calculations tonight using masses, atomic masses, molar masses, formula masses. We learned about percent composition. We learned how to use percent composition to determine empirical formula. We learned what an empirical formula is, if you're unsure about that. We learned how to calculate molar mass. We learned about where molar masses come from. We learned about what the mole is, Avogadro's number, all kinds of fun stuff. All right. So for all of my students who are out there, are there any questions? We've covered quite a bit of ground tonight. And if you're looking at my slides and thinking, dang, we're pretty far ahead, you're right. We've gotten quite a bit ahead in chapter 3. In fact, I don't even have that much left in chapter 3. Who would enjoy a night, some night we just do review? We just do practice problems from start to finish. Anyone? Yes, please. Okay, good. All right. Even if it's just Brittany. Perfect. All right. Deanna's on board too. Chris, great. Trevor, excellent. Practice problems before the exam. So remember, I always post a practice exam. Before the first exam, I went over the entire practice exam with you. So, but remember, you have to help me, okay? I can't go into your brain and make you learn. You're never going to learn it just by listening to me and watching me solve problems. I can tell you that right now. You could sit here and watch me solve problems for 100 years and you wouldn't be able to do it, okay? You have to sit down alone with one of these, okay? This is called paper. You have to sit down alone with a piece of paper and a pencil and one of these. This is called a calculator. I'm being sarcastic, but you get my drift, okay? Maybe I should stop recording this.